So today is October 8th, and you're here for Econ 249 for statistics. And what you're looking at is a flyer that I received from one of your peers who's a part of this very important organization. So they're having a wellness seminar tonight from 6 to 7:30. In the chat box, I've also put in the Zoom link. And it's hosted by these companies, so you should get involved with attending professional workshops, and it's free. So if you have any questions, you can email me and I will put you in touch with the students who are helping to organize this. Does anyone have any questions about the material we just covered in the last class on Tuesday? Okay, just before class today, I emailed all the groups with your scores for the Excel number 2 assignment. If you did not receive an email from me, it's probably because I emailed from Blackboard. So it's the email that you registered with on Blackboard. If you didn't receive an email, then contact your teammates and they can tell you what the score is. So this time it was out of 8 points because there were more questions to be answered. Most of you did fairly well. Again, if you have questions about the scoring, send me an email. Okay. Rad, do you have a question?
Yes, Professor. I just wanted to ask how many more Excel assignments we'll have?
I think it's 1 or 2.
Okay.
So Excel number 3, I'm going to give you on Tuesday, and then I'm not sure about Excel 4. So let's see how things go.
Okay, thanks.
Okay. So we're going to continue with chapter 6. And if you recall, chapter 6 was about random variables and probability models. And in the last class, I started with a video, and I assumed that you could hear what I hear, but I guess Blackboard doesn't have that function. So I gave you the link to watch the video on your own. It's just the first 5 minutes, and it kind of introduces this idea of using probability in the real world. What we did in the last class was look at probability models in general. And I said that once you have listed all the values of X and the probabilities associated with X, then you have a probability model or a probability distribution. And then we went on to talk about how to calculate expected value. What would you expect a certain value of X to be? And that's the formula we used. And then we also discussed how to get standard deviation of that discrete random variable X. And this is the formula that we used. And we applied it to an example about an insurance company. And then you did one on your own where you calculated probabilities, well, not probabilities, but expected value and standard deviation for this example, bookstore purchases. And then we ended the class by talking about what if you have a constant and you add it to your expected value or you add it to your standard deviation, and what if you had a constant that you multiplied to your expected value or your standard deviation. So that's where we ended. Today we're going to start something different. So if the last class focused on probability distributions in general, today's class is going to focus specifically on discrete probability distributions. Now, again, if you recall, I said that chapter 6 will be talking about discrete probability distributions. The next chapter, chapter 7, will focus on continuous probability distributions. So now, what's the meaning of discrete? What's the meaning of discrete? Do you remember?
The numbers are integers or counting numbers.
Yes, perfect. They're integers. Oscar, you're right too. Red, you're correct. Xiao Ting, counting numbers. So 0, 1, 2, 3, and so on. So continuous probability distributions in the next chapter will deal with values that are non-integers, measurements, precise values with a decimal or a fraction. Okay, so there's 4 types of discrete probability distributions: uniform distribution, geometric distribution, binomial, and Poisson. Of the 4, binomial distribution is really the most important one that we'll talk about. So I'm going to start with uniform distribution or the uniform model. Now, we're not going to study the uniform model. It's there, but we're not going to study it. Why not?
Sorry, what was
Because
the last distribution?
let's go back. So uniform,
Poisson. Thank you.
geometric, binomial, and Poisson. So starting with the uniform model, we will not be focusing on the uniform model. Why? Because it's not practical. It's the simplest model. It talks about outcomes being equally likely. So for example, if I had to draw the distribution, I would have a histogram that looks something like this, where the probabilities are listed on the y-axis and it's all uniform. The probabilities are all the same. So it doesn't really happen in real life where you have equal probabilities. So this is too simple of a model, so I don't spend time on this. Moving on to the next model is the geometric model. Again, the geometric model, we will not discuss it. Why not? Because it's actually quite complicated for this course. But if you're interested, let me just give you a couple of sentences about it. With the geometric model, you're trying to figure out how long it takes to achieve the first success. How long it takes to achieve the first success. So first of all, what do I mean by success? Success doesn't necessarily mean a positive thing. It means the desired outcome. So the desired outcome would be considered a success. So how long does it take to achieve that desired outcome? So how long it takes means how many trials? How many trials before I can achieve that first success? So like I said, it can get complicated because you have to include many different factors. An example I can give you is, let's say Google acquires some new software. And usually when there's this new software, they check it for all kinds of bugs, and they don't purchase it unless it's free of all that stuff. But Google wants to know after how many trials will a bug be discovered? Because at some point, a bug will be discovered. So Google wants to know after how many trials. So if the expected number of trials until the bug is discovered is quite high, that means it takes a long time, or it takes many trials by the time they discover a bug, then Google might decide to release the software. If it's only a few trials, then they might decide not to purchase it or not release it. So this is an example of using geometric distribution. Okay, so we're not going to study this. We're not going to focus on geometric. I'm going to move on to the Poisson model. So first I'll read: predicting the number of events that occur over a given interval of time or space. The Poisson model is a good model to consider whenever the data consist of counts of occurrences. So first of all, this name, Poisson, is named after a French, I think, mathematician, Simeon Poisson. And he was interested in different kinds of probabilities and probability models. In fact, he was very interested in studying rare events, events that would hardly happen. Okay, so studying the probability of something that is highly unlikely. So now we understand this is a discrete probability model, meaning the values of x are discrete values, but it's quite specific. So let's see here. Predicting the number of events. Okay, so this is my value for X. Is it 0 events, 1 event, 2 event? And when I say event, it's that desired outcome, right? So when X is 0, when X is 32, when X is 506. So predicting that, the Poisson model is very specific. It only considers an interval of time or space, a given interval of time or space. So it's not just interested in predicting an outcome or predicting the number of events. It predicts the number of events in a specific interval of time or space. So let me give you an example. Let's say by Niagara Falls, by the border, we know that an average of 96 trucks arrive at the border crossing every hour. Okay, I'm just making that number up. I don't know if it's true. But let's say at the border, we know an average of 96 trucks arrive at the border crossing every hour. So you're asked to find the probability of 100 trucks arriving at the border crossing every hour. What's the probability of 100 trucks arriving at the border crossing every hour? Now, how do I know that I'm going to use a Poisson distribution or a Poisson model? What is it that I said in that example that relates to what I have marked here on this slide?
The number of occurrences over.
Not the number of occurrences. So not
It's between a given
predicting.
time frame.
Yes, so Oscar, you're right, Rad, you're right, Shubham, it's the time. So specifically, I said crossing every hour. So you have
Oh,
to
I
be
missed that.
able
Sorry.
to, yeah, no worries. So you have to be able to identify what the time or the space is. So specifically asked every hour. So that's your interval of time. Okay, I'll give you another example. The textbook you're using is a 2019 version, and the publishing company wants to come out with a new version in 2021. The publishing company already knows that the number of typos in a new textbook edition averages about 1.5 errors per 100 pages. Okay, they already know this. They know that the number of typos in a new textbook edition averages about 1.5 errors per 100 pages. So the employees of the company want to calculate what's the probability of 0 errors in this new textbook edition for 2021. How do you know this is a Poisson model or going to follow a Poisson model?
There's a number of errors per page.
Right, per 100 pages. Yep, that's it. So that was your space. Yes, Christopher, that's right. So in that case, it was the interval of space. So again, the examples are very specific to time or space. Okay, so why do I keep talking about
Excuse me,
averages?
Professor.
Uh-huh, go
I
ahead.
have a question. So I want to know why this one is different than the last model. Is it because we already know what the rate of error is in a set period?
So the last one, we're not going to be doing any problems for geometric model, and we're
Okay.
not doing any problems for uniform model. For Poisson model, for this one, I'm about to show you how to calculate the probability, and in that formula, you're going to need the value for average. So that's why I kept mentioning the average number of trucks that arrived, the average number of typos. So I'll show you. I'll explain in a moment here.
Okay.
So that's a good question. So I'm going to rewrite what you see on the screen because there's too much going on here. So I'm saying if I want to calculate the probability of X, so let's say the probability of 100 trucks arriving at that border crossing every hour, what's the formula I'm going to use? Well, I know it's a Poisson model, so I'm going to use the Poisson model formula, which was discovered by Simeon Poisson, right? Okay, so the numerator is e raised to the power negative mu times mu raised to the power x, the whole thing divided by x factorial. So you can see here a lot going on, but it's not very different from what's in this little green box. Instead of lambda, which they have written, I'm using mu. Does anyone remember what mu stands for? Expected value, or in other words, population mean. Yep, population mean, same thing, okay? So instead of using lambda, we're going to use mu. X is the number of occurrences. So number of occurrences meaning the number of events that occur in a given interval of time or space, that desired outcome. So either it's number of trucks crossing the border every hour, or the number of typos per 100 pages. Okay, so now, okay, we're going, in the next slide, I'm going to do an example where we plug these values in, but let me tell you first what's E. So this variable E is actually a constant. It's like pi. It never changes. So let me write the value for E here. E is equal to 2.71828. So that value of E is always 2.71828. It never changes. Okay, it's a constant. Mu is the average. So when I gave you those averages, you would have to plug that into this formula. So you need to be given the average for that experiment. And then X is whatever you're trying to find. So if I want to know what if there are 0 errors, then X would be 0. What if there are 100 trucks crossing, then X would be 100. And then this little thing here, like an exclamation mark, does anyone remember what factorial means? Because that's factorial, X factorial. So you might have seen it in some math class
It's
before.
x times x minus 1 times x minus 2 times x minus 3.
Okay, so if I said 3 factorial, what does that mean?
That would be 3 times 2 times 1 until
Yep,
it reaches
exactly.
0.
Yep. So not 0, right? 3 times
Not
2
0.
times 1. Yeah. So if I gave you 100 trucks, what's the probability of 100 trucks? And you had to do x factorial, that would be 100 times 99 times 98 times all the way to 1. So now with a Poisson model, what if you have to calculate expected value and standard deviation? Okay, so let's continue before we start applying this to an actual problem. Expected value is your mean, right? That never changed. Standard deviation. So I'm going to write this differently. And I want you to note this in your notes, that sigma squared is always equal to mu. And this is only true for a Poisson model. Sigma squared is always equal to mu. So what's sigma squared? Sigma squared is your variance. Variance is always equal to population mean when you're dealing with a Poisson model. This is not true for any other distribution. Okay, so you have to remember that sigma squared is equal to mu. Okay, I'm moving to the next slide. Any questions? So let's look at this example. A website averages 4 hits per minute. Find the probability that there will be no hits in the next minute. So let's think about it first. A website averages 4 hits per minute. First of all, why am I using a Poisson model? I know that I'm going to use a Poisson model. The reason is why. Set rate in set time, time frame is 4 minutes. Interval of time. So let's go with Priscilla's answer. Per minute, right? That's an interval of time. Yes, Gilbert. So what's my desired outcome? Or in other words, what does X stand for? So before I try to calculate what X is, just in general, what does X stand for? What's my desired outcome? What's the success I'm interested in?
No hits in the next minute.
Right. Hits per minute. That's it. Yeah. So I need to find the probability of no hits in the next minute. That's right. But I just want to know at this point, what does X stand for? X stands for a discrete random variable, the number of hits per minute. So X could be 0 hits, 1 hit, 4 hits, 18 hits per minute. It could be anything, right? Okay, so now I'm going to find the probability that X will have no hits. Okay, so I know you have the values here, but I'm going to rewrite the formula because you need to know where these numbers are coming from. So the formula says it's e raised to the power negative mu times mu raised to the power x divided by x factorial. Now you don't need to use Excel for this because the problems for Poisson distribution are quite simple. You can plug into the formula, use your calculator and get the answer. I'll tell you when you really need to use Excel, and that will be for the next distribution. Okay, so next thing is to plug in the values. We know that E is always going to be 2.71828 raised to the power, and what's mu over here? Negative mu. What's mu? Oscar, you say 4. Okay, so times 4, and x is raised to the power 0. Yep, Diana, you're right. And then x factorial means 0 factorial. Okay, next step. Now, a number raised to the power 0 is equal to what? A number raised to the power 0 is always equal to 1. Yes, Hirak, Oscar, Jeffrey, you're right. So this value is equal to 1. Does anyone remember what the math rule is for 0 factorial? So we said 3 factorial is 3 times 2 times 1. 1 factorial is 1. What is 0 factorial? Not 0. So Ying, it's not 0. Oscar, you're right. It's 1. Yep. Ying, that's right. So it's 1. So now my numerator is 1. My denominator is 1. I am left with 2.71828 raised to the power negative 4. So now a number raised to a negative exponent just means that I do 1 over 2.718 raised to the power 4. So now you can use your calculator for this. It's quite simple. You do 2.71828 times 2.718 times 2.7 times 2. Get that value, then 1 over that, and then this is your answer, right? 0.0183. So to answer that question, find the probability that there will be no hits in the next minute. Well, that probability is 1.83%. The probability of no hits is 1.83%. So again, not difficult. You just need to be aware of whether or not this is a Poisson model, what the average is. Yeah. Questions for me? Okay, so I'm going to move on to the next slide, and you're going to do the same thing on your own. But first, let me set this up for you. So the question says, a website manager has noticed that during evening hours, about 3 people per minute check out from their online shopping cart and make a purchase. She believes that each purchase is independent of the others. Okay, so
Can we assume evening hours is 6 p.m. to 6 a.m. in this question?
it
Or does that not
does
matter?
not matter.
Okay.
Does not matter because I'm concerned about this, the per minute. So that's telling me that, okay, there's some interval of time that they're only specifically interested in. So that's my clue that it's a Poisson model. The other thing, it's telling me about 3 people. So that about 3 people means an average. Okay. So this is what we know about 3 people per minute check out from their online shopping cart and make a purchase. The question also says she believes that each purchase is independent of the others. Now, why do we need to know that? What does that mean? Each purchase is independent of the others. No bias, shouting. Okay, if there's no bias, what exactly does that mean? Outcome of one doesn't influence the outcome of another. Shubham, you say there's no connection. Okay, right. So what happens first is not going to affect what happens next or what happened previously. Okay, agreed. And we need to know that because if there's some kind of bias or if there's some connection with the purchases, that's going to affect how we calculate probability. And it gets complicated because we need to include those factors. How much of an influence is there? So we can't use this model. So we have to assume that they are independent. Okay, so I think we answered the first question already. So we'll skip that question. Next question says, what is the probability that no one makes a purchase in the next minute? Okay, so I'm going to first write the formula for you because it's on the previous slide. So P of X is equal to E raised to the power negative mu times mu raised to the power x divided by x factorial. And I'll also give you the value for E. E is always equal to and now I'm going to give you the question in a poll. Okay, so you should see it now. Okay, another minute. Okay, 30 seconds. Okay, and I'm going to stop the poll. Okay, it's stopping here. Okay, so most of you chose answer choice 2, and most of you are right. So let's see. If you had to plug it in, E is 2.71828. So let's see if I can write it here. Yeah. So we're saying makes no purchase, so X is 0, is equal to raised to the power, what's mu? 3. Okay, so we know about 3 people times 3 raised to the power, and X is 0 divided by 0 factorial. So yes, 3 raised to the power 0 is 1, 0 factorial is 1, so I'm left with 1 over 2.71828 raised to the power 3. And yes, that answer is then B. Let's look at the next question. What is the probability that in any 1 minute, at least one purchase is made? In any 1 minute is also another way of saying per minute. So what is the probability that at least one purchase is made? Okay, so I'll help you out first. I'm saying find the probability that at least one purchase. Okay, and then I'll give you a moment to do that, and then we'll work on it together. So I'm typing answer choices here. Okay, so you have a minute. So I'll work on it with you right after the polling. Okay, stopping the poll here. Okay. So most of you chose 0.9502, and that answer is correct. But let's see how we can get that answer. So the question is saying, what is the probability that in any 1 minute, at least one purchase is made? At least one. That means the minimum is 1. That means it has to be greater than or equal to 1. So I have to find probability of x greater than or equal to 1. Okay, that means greater than or equal to 1, which means the probability when x is, so let me write it here first. So we start when there are 0 purchases, 1 purchase, 2 purchases, 3 purchases, and I can go on. Should I stop at 3? Should I stop at 3 purchases or go on to more? So Oscar, you're right. I should go on to more. The 3 purchases is just an average that they gave me. So I can go on to 4 purchases a minute, 5 purchases a minute. I don't know when to stop. They could have 100 purchases. They could have 62 purchases. I don't know. There's no ending number here. In the second question, I calculated the value for probability when x is equal to 0. I found out that that value is 0.0498. Okay, so that we know. Now I have to find the probability when x is greater than or equal to 1. Greater than or equal to 1 means I have to include 1 and everything after 1. But that's going to take a long time and it's quite complicated because I don't know where to stop. So Rad, you pointed out that you could do 1, which is the sum of all my probabilities, so 1.00. Take 1.00 and subtract it from 0.0498. So what I'm doing is take, so let's cross this off, okay, and take 1 minus the probability when x is equal to 0. So that's 1 minus 0.0498, and that answer is C. So that's how you get that answer. So be very familiar with this at least, at most. There's a lot of problems in your homework that refer to this. And it's not always greater than, less than, 1 purchase, not always equal to. It could be at least or at most. Okay, any questions about this? So this is all about the Poisson distribution. Again, we didn't need Excel because this is a fairly simple problem. You can do it with a calculator. You just have to recognize that you can use the properties of a probability distribution. Okay, so I'm moving on to the next slide. Just making sure. Okay, so the next slide is about the binomial model or the binomial distribution. Now remember, this is the 4th type of discrete probability distribution. The first 2 we didn't study, the Poisson we just completed. So the binomial model predicts the number of successes. Now there's that word again, success. So a success is your desired outcome. Again, it doesn't mean that it's something positive, it's just what you want the outcome to be, what you're interested in. So the binomial model is used a lot in many different industries. I'll give you a few examples first before I talk about the properties of a binomial distribution. For example, when you toss a coin, you can get two outcomes, right? Heads or tails. That's once you set up all the probabilities that are associated with X, that method of calculating probability is a binomial, will follow a binomial model. Another example is if you send out a survey and the questions have yes or no responses. The probability of getting no responses, for example, maybe probability of getting 0 no responses or probability of getting 50 no responses, that method is a binomial probability distribution. Third example, shooting free throws in basketball. So either it goes in or it doesn't go in, right? So again, binomial model. So you might be seeing some kind of pattern here with all the examples I'm giving you, and I'll go back to that pattern when I talk about the properties now. So you need to know the properties of a binomial distribution. So this you would have to study or know where to refer to when you're taking the next exam. Number one, the sample has n observations. Okay, this is not something new. This you already know. When we say n, we're talking about sample size. So the number of observations in your sample size. Two, each observation can result in only one of two possible outcomes, success and failure for each trial. So every time you have a trial or an attempt, whether you're tossing your coin or you're sending out yes/no responses in a survey, or you're shooting a free throw in basketball, there's only two possible outcomes, either a success or a failure. A success might be all the no responses because that's your desired outcome. A failure could be heads because you're only interested in the number of tails. Okay, so that's where that pattern comes in. Two possible outcomes in a binomial model. Number three, the proportion of success denoted by P is the same for each trial. So this P is not probability, it's proportion of success. And the proportion of failure is denoted by Q, which is 1 minus P. In your homework, they use Q as a proportion of failure, but I like to use 1 minus P because then that's one less variable for you to remember. Okay, so what this property is saying that every time you have a trial, every time you toss that coin, or every time you throw a basketball free throw, it's always going to be the same proportion of success. One success out of two possible outcomes, or one success out of four possible outcomes, whatever it is. So it never changes. Number four, the property number four says the outcome of any observation is independent of another observation. Now we defined what independence means. It's saying that the outcome of one is not going to affect the outcome of another. But why do you think these outcomes are independent? Why do you think we're saying yes or no responses on a survey are considered independent? How could they be independent? So that's really my question. How could they be dependent?
One does not affect the other.
Okay, so we know that already. One doesn't affect the other, but how? How come one response does not affect the other? Everyone has their own opinion. Yes, Diana, you're very, very close.
They're opposites.
Not necessarily. So I'm trying to get to the point of random selection. They were randomly selected when they were given the survey, so there's no bias involved. They have their own opinions. They're not going to influence each other, affect each other. So that's a property of the binomial distribution. We have to assume that exists. Otherwise, we cannot use the binomial distribution. It gets complicated. Okay, so that's the fourth property. And the fifth property says the binomial variable x is the number of successes in n observations. So that's just a statement. Whenever we use x, we're referring to a binomial variable. Remember, x is our random variable. It's discrete. Values are 0, 1, 2, 3, and so on. So it could be 0 successes, 23 successes in our sample size of n. So I said that the binomial model is used a lot in many different industries. I'll give you a quick example. Businesses, a common source of business data is an opinion or a preference survey. So they collect this data by sending out these surveys. And many of these surveys have only two responses, two alternative responses. You could say yes or you could say no in the survey. Maybe the business is interested in all the yes responses. So if you collect the number of yes responses and calculate the probabilities of having 0 yes responses or 55 yes responses, that's going to have a binomial distribution. So it's very commonly used and it's quite important to understand. So you can see a small difference here with the binomial model compared to the Poisson model. They're both really looking at a certain specific desired outcome, but the Poisson model was in an interval of time or space. The binomial model has nothing to do with that. Okay, it doesn't refer to any particular time or space. One more thing about the properties of a binomial distribution. If your experiment or your phenomenon satisfies properties number 2, 3, and 4, then we say that it has completed a Bernoulli trial, a Bernoulli trial. So Bernoulli is named after Daniel Bernoulli, who was a Swiss mathematician, and he was known for his work in probability and statistics. So he actually came out with this set of properties and was able to prove that a binomial model has these three properties, properties number 2, 3, and 4, that every observation will have only one of two possible outcomes, either a success or a failure. The proportion of success never changes every time you have a new trial, and the outcomes are independent of each other. So there are some examples or exercises in your homework where they give you an example and ask whether or not it satisfies a Bernoulli trial. So that means you need to know where to refer to in your slides to make sure that it has satisfied each of these three properties. Okay. So moving on, here's the formula. Now it looks kind of complicated to use a binomial model formula, and I'm going to rewrite it at the bottom. Probability of x. So if you had to find the probability of a specific number of successes, and you know you're dealing with a binomial distribution, the formula says the numerator starts with n factorial divided by n minus x, the whole thing factorial, times x factorial times p raised to the power x times 1 minus p raised to the power n minus x. So you can see here it's quite a long formula, but it's not really complicated. Let's look at what everything means. So n is your number of observations. We have that in our sample size. How many times you took those free throws in basketball, for example. P here is your proportion of success. I know it says probability, but it's proportion of success. And then Q would be, instead of writing Q, I'm writing 1 minus P, which is the proportion of failure. Okay, so that's where that comes in. Next thing is X. X is your number of successes. So that's what you're trying to find, x. And now we know what factorial means. That being said, if we had class in a classroom and I was writing on the board, I would write this formula on the board. If you had a test in the classroom, you would be plugging this formula into your test question to calculate binomial probabilities. But since we're doing everything online, I'm going to show you how to do this using Excel. So you're not required to know this formula or plug in the values using this formula. You're going to need to know how to use Excel. So I will show that to you in a moment. But before we continue, let me show you the mean and standard deviation. Okay, so remember, mean and standard deviation, the formula is different for each of the two different probabilities I showed you. So we just did Poisson model, it has a different formula, and now binomial model. So the mean is straightforward, right? It's n times p, that's all it is. If I asked you to find the mean, and you know it's a binomial distribution, n times p. Standard deviation, I'm going to rewrite it because I don't like it with a q. So that's equal to n times p times 1 minus p. And then don't forget to square root because otherwise you would get variance. So that's the formula for standard deviation. Okay, so moving on. That's exactly what I just wrote. And here's the formula in Excel. So we're going to do an example now, and I'm going to use this formula in Excel. So remember, this formula is available to you on this slide in chapter 6. So don't go searching for this. Use this formula when you're doing the homework. Okay, so here's our example. The example says you toss a fair coin 3 times. Let x equal number of tails. Okay, couple of things first. Toss a fair coin. Why should I say it's fair? Well, I'm saying it's fair because it's not a trick coin, it's a fair coin. There's only heads on one side and tails on one side. So I have to specify that it's not a trick coin. I'm tossing it 3 times and I'm only interested in tails. The question says, let x equal number of tails. So I'm going to switch my screen to Excel and continue with this problem showing you Excel. Okay, so you should be able to see this. So you can see I started with 2 columns, x and p of x, right? So that's my whole goal, that I'm going to set up a probability model. So first thing is, what does x stand for? And I'll write it here. So my question is, what does x stand for? I don't know why I wrote C, but so x should be the number of tails. X is my number of tails. Okay, so I'm told that my coin is tossed 3 times. So I toss it, okay, so if I toss it 3 times, then I'm saying n is equal to 3. Okay, I need to know my proportion of success. So my proportion of success. Any idea what my proportion of success is? So every time I
0.5.
toss, yeah. How did you get that?
It's a fair coin, and it said p equals 0.5 in the example.
Okay, so without looking at the
It's a
answer,
coin, it only has 2 sides.
right,
One
yeah.
for the other.
So even if P was not given to you, you could have found it out. I can only get one tail out of two possible outcomes. So that means 1 out of 2, so that means 0.5 or 50%. So the proportion of success is 0.5. So every time I toss that coin, I'm always going to get zero point 0.5, right? That's my proportion. It's always going to be one tail out of two possible outcomes. Why do I keep saying tails? Because that's my desired outcome, tails. Okay, so now I know X, I know N, and I know P. So just going back to the question here, the question asks me to calculate, let's see, let's go back here. So toss a fair coin 3 times, let X equal number of tails. So X, this line, this little squiggly line is read as is distributed. So that's what it says. X is distributed binomially with n equal 3 and p equal 0.5. X is distributed binomially with n equal 3 and p equal 0.5. So that's given to you in the question, but yes, you could have found it out. And then they ask you to find the probability when x is equal to 0, probability when x is equal to 1, x is equal to 2, x is equal to 3. So if you had to do it manually, you would plug it into this formula, but we're going to use Excel, right? So Judah, let's see if your answers are correct. I'm going to share my Excel screen again. Okay, so we're here. So I had to find the probability when x is equal to 0, probability when x is equal to 1, 2, and 3. And I stop at 3 because I only tossed that coin 3 times. Okay, now to plug in the formula. So this is the formula, right? Excel already knows how to calculate binomial distribution. So I put an equal sign, then I type in binom dist, open parentheses, and instead of typing x, I select that cell, and that happens to be cell A2. That's the value of x that I'm going to use, comma, n is 3, I already know that, and p is my proportion of success, which we found out is 0.5, and then I type the word false. Now, why false and why not true? Well, if I type false, then Excel gives me the probability of this binomial distribution just for the value of that x. If I type true, it gives me a cumulative probability, which is not what I want. Okay, so that's why we have false, and I hit enter, and that's the same probability that you calculated, Judah. And then I'm going to drag this all the way down, and that's right. So when x is 0, the probability is 0.125, when x is 1, 0.375, and so on. Any questions for me? So I have a couple of questions about what we just calculated here, and I'm going to type it into my Excel spreadsheet. So my first question is, what's the probability when the x is, maybe I can use a symbol here, x is greater than or equal to 0. Okay. So what do you think I should do? Find the probability when x is greater than or equal to 0. Nope.
Or equal to.
Yeah.
Right?
Yep.
So it's 1. That's all
Yeah.
possibilities.
Right. Exactly. So Oscar, you're right. So I'm typing it. So if x is greater than or equal to 0, then I'm saying when x is equal to 0 plus when x equal to 1 plus everything all the way down, greater than and including 0. So that's equal to, and how do we know that? it's the sum, right? So I hit sum of all this, and that's equal to 1. So that answer is equal to 1. Let's do another one. Find the probability when x is less than or equal to 1. Probability when x is less than or equal to 1. So Nayang, Judah, Ying, Christopher, I think you're all right. Let's go back and see this. Okay, so this is saying probability when x is equal to 1 plus everything less than 1, which means x is equal to 0. So when it's equal to 1, that value is 0.375, plus when it's equal to 0, it's 0.125, which is equal to 0.5. Yes, so that's correct. Let me fix that. Any questions for me? Let's do another one. What's the probability of tossing this coin 3 times and then getting at least 2 tails? What's the probability of getting at least 2 tails? Okay, tell us how you got that.
It's the possibility of 2 and the possibility of 3. So it's 0.375 plus 125.
3.0.375 plus 0.125 is equal to 0.5. Yes. So at least 2 means the minimum is 2. So 2 and everything beyond 2. So probability when x is equal to 2 plus probability when x is equal to 3. So you would add those two probabilities and get the answer. Yep. Any questions for me? Okay, one last thing. So remember, I wonder if I can copy and paste onto a whiteboard. So let's see, I'm going to copy this and bring this over and stop sharing. And then I want to show you a blank whiteboard, and I cannot paste. Okay, never mind. So I'm going to draw a graph of what it is we just calculated, our probabilities, right? So let's say my x-axis is the number of tails, and my y-axis is all the probabilities that we calculated. So we said that x could be 0, 1, 2, 3. Okay, and then we had the values for our probabilities. Just making sure I have the same values. 0.125, 0.375. Okay. So if I put my points on the graph, when x is 0, it was 0.125, and x is 1, 0.375, and x is 2, 0.375, x is 3. And now if I draw my graph, I get something like this. I kind of missed it there, but something like this. So this is telling me that my binomial distribution is symmetric. So for my binomial distribution to be symmetric, it's because my proportion of success is equal to 0.5. Whenever your proportion of success is equal to 0.5, then you will always have a symmetric distribution. If it is not equal to 0.5, then you have a skewed distribution. It doesn't matter left skewed or right skewed. It's skewed. Okay, so now going back to our slides, that brings us to the last slide for today, which is about the shape or the characteristics of a binomial distribution. So this is what I just mentioned. When p is equal to 0.5, you always have a symmetric binomial distribution. If it's not 0.5, it's skewed. Next thing is mean. So I said that this is the formula, n times p. So if I plug in the values from my coin toss, n was equal to 3 and p was 0.5. So can someone give us the value for the mean? What's the average number of tails that you could guess when the average number of tails that you could get when you toss this coin 3 times? Okay, thank you, Diana. It's 1.5. And then let's do standard deviation. So standard deviation is this formula. And what do you get for that? So it's the square root, and don't forget to square root because otherwise it's not standard deviation. N times p times 1 minus p. Anyone answer for us? Yu Jiang, 0.866, okay. Iraq, you have the same thing, okay. Yep, so standard deviation is this. So this is saying that when you toss this coin 3 times, you should expect to get 1.5 tails, plus or minus standard deviation of 0.866. So this is it for this chapter. There's one more slide giving you practice to try another problem on your own, but I'm not going to do it in class. I think you have enough material to finish your homework. And that's it. If you have any questions, I can stay for a couple of minutes, but enjoy the weekend.